This video goes over some more examples of permutations. Every day in real life, we encounter problems which ask us how many ways can we solve a situation, or how many ways can we organize items. And so we're going to look at a couple more examples to practice doing that. So here, how many ways, so permutations, can we arrange 9 students? So I've got 9 objects to choose from, which is my n, and my line is going to also have a length of 9. So that means that my number of permutations are n permute 9 permute 9, which is 9 factorial, which is going to give me 362,880 ways to arrange those students in a line. The next one is going to ask me about the word tsunami, but I need to know how many arrangements begin with a consonant. So the first thing I need to know is what is a consonant, not a vowel. So not A, E, I, O, or U. So we're going to count how many consonants we have in the word tsunami. So T, S, N, and M are all consonants. So I've got 4 consonants. And so what I'm going to do is keep my first position fixed, but I've got 4 options for that first position. So that would be like 4 branches on a tree diagram. So I've got 4 options for my first position, and then left over is 6 spots to choose from. So tsunami has 7 letters. What I'm doing is making the first one fixed. It has to be a consonant. There are 4 possibilities for that. And then I'm going to arrange the other 6 letters in any way that I want to. It doesn't matter if it's a consonant or a vowel. So I've got 6 objects to choose from and a length of 6, the linear setup that I'm creating. So 4 times 6 factorial will give me 2,880 different arrangements of the word tsunami that begin with a consonant. The last 2 examples here are a little bit more work with factorials. So example 3, we're just going to expand. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. M factorial is m times m minus 1 times m minus 2 times m minus 3 all the way down to 3, 2, and then 1. And then a plus 1 factorial works almost the same, except we're going to start at a, then we take away 1, so we get a, then we take away 1 again, we get a minus 1 times a minus 2. But just like the first one, this goes all the way down to 3, 2, and 1. Now we've got 54 factorial. Please don't write all of those down. You only need a couple at the beginning and a couple at the end. 3, 2, 1. Example 4 is going to ask us to simplify some expressions for factorial. So what I want to do is expand the top until I get to what I see on the bottom. So I've got a plus 2. I'm going to take away 1 for my next term, a plus 1. And then I'm going to take away another. I'm going to notice that on the bottom I have a factorial. So I'm going to stop here. So a plus 2 factorial is the same as a plus 2 times a plus 1 times a factorial. In my denominator, I also have a factorial. That is just a number, so I can cancel it out. And what I'm left over with is a plus 2 times a plus 1. And I'm going to leave it in that factored form. Example B here, I'm going to notice that even though my denominator seems a little bit more complicated, it starts at a lower value than my numerator does. So what I'm going to do is expand my numerator until it looks the same as my denominator. So that means going all the way down to a minus 3, summarizing the rest with factorial, And then I've got a minus 3 factorial on the bottom. So same as in example A minus 3 factorial and a minus 3 factorial are just numbers, so they cancel out. And then what I'm left with is a times a minus 1 times a minus 2, which is equivalent to the expression on the left-hand side that has factorials. This technique is useful when you are solving equations or when you're trying to substitute in different values. Having a representation of the expression without a factorial in it makes your algebra a lot easier.